Okay, last little bit, just kind of wrapping up this whole week on energy. A little bit more on heat before we leave it. There's three ways that heat kind of moves around. Heat energy kind of moves. One is conduction. Hopefully, you've got an idea about what conduction is. One is convection, and one's radiation. Uh, One of them explains like the cool visual of a lava lamp, if you know what a lava lamp is. One of them kind of explains how like a hot air balloon rises. Uh, One of those three words talks about how when a medium gets hot, it becomes less dense and it starts to float. That is convection. Convection is how heat kind of moves around because the actual material would move around. Hot air rises. In a convection oven, they put a fan on so that the fan will blow the hot air around. But convection is like the fluid, the air, if it's a liquid, how the hot stuff rises to the top. Conduction is why we use wooden spoons instead of metal spoons, how heat energy moves through materials. When heat energy moves through materials, we call those materials conductors versus insulators. Nice day to have a hot chocolate today. If you put a spoon into hot water, the particles of the spoon pick up the energy and they literally vibrate a little bit faster and they bump that energy along through the length of the spoon. So if you left a spoon in hot water for too long, the handle of the spoon, a metal spoon, would get hot. If you used a wooden stir stick or something, wood is an insulator. The particles don't bop around and pass that energy along the same way. Conduction is when the energy is moving through the material, just sort of like a domino effect, bumping into each other particles and moving the energy along. Where convection is the material actually moves. A chunk of hot air will rise and heat up the air in another spot. Convection shows up in weather patterns, shows up in like furnace systems where conduction would show up in materials, like how energy bumps along through. Like if you're designing a better cooler or a better coffee mug, you would worry about conduction and insulation. If you're designing a furnace or looking at weather, you would look at convection. The last one, the last important word is radiation. Radiation is how heat travels through space. Space could literally be space, like outer space, how the heat energy gets from the sun to us on Earth. It could be air, like if you're standing in front of a campfire or a wooded, a fire burning stove, how the heat comes off that campfire and hits the front of you, just almost like light. Um, it's it's a cool physics thing we don't have to get into, but heat is infrared, so it's infrared light waves, how they travel. The proper metric unit that we're going to be using in physics is Celsius, but there's some older ones too. Um, there's one called Kelvin. Um, Sorry, Kelvin's a newer one. There's one called Kelvin, named after a person. There's another one called Fahrenheit, named after, that's the older one, that's named after a person. Um, Celsius was based on the boiling point of water, boiling point and freezing point. Basically, Mr. Celsius said, let's say 0 degrees Celsius is where water freezes, and 100 degrees Celsius is where water boils. And we're just going to divide it up evenly in between into 100 degrees. The older one, Fahrenheit, I've heard a few stories about this, but I heard that it was based on salt water. People sailing in the oceans, they picked the freezing point and boiling point. I'm not sure if that part's exactly right, but it was based on something to do with salt water. The issue with Fahrenheit, why I find that inconvenient, and I think why people eventually left it, is how you're going to base something on salt water. Like, how salty is the water? It could be really salty, like the Dead Sea, or it could be not very salty. So, basing a unit on something arbitrary like salt water wasn't the best idea. And then the one that maybe you've come across in your chemistry classes, Kelvin, it's very similar to Celsius. Um, but they just based it off of absolute zero. Absolute zero is that concept in chemistry, the coldest that something can get to, where those vibrating particles actually stop vibrating. They call that absolute zero. I don't think you have to memorize it. This should just be stuff. If we got to go to Celsius, sorry, if we're from Celsius and we want to go to Kelvin, basically the set is that 0 Kelvin is absolute zero, which is negative 273 degrees Kelvin. So if we want to go from Celsius to Kelvin, we have to add 273.15. That just the degrees are equal. If you change 10 degrees Kelvin, that's the same as changing 10 degrees Celsius. The steps are equal. They just changed where the zero was. 0 Celsius is where water freezes. 0 Kelvin is absolute zero. Fahrenheit, a little bit messier. I've already typed it. To convert, we're going to multiply by 9/5, which is roughly 2, and then add on 32. So just one last quick one, and then we'll call it quits for this week. Let's say we had 20 degrees Celsius. To get that 2 Kelvin, sorry, a little bit messy. To get it 2 Kelvin isn't really that hard. We just literally have to add that 273 number. And that kind of resets the scale. So 20 plus 273.15. It's been a long lesson, but a little bit of mental math. That is 293.15 K for Kelvin. If we want to put that to Fahrenheit for some reason, oops, I can never remember how to spell Fahrenheit. Fahrenheit. We're going to multiply by 9/5, and then we're going to add 32. So 20 degrees multiplied by 9/5 plus 32 equals, if you do the math on that, the 20 times 9/5 is 4 times 9 is 36. 36 plus 32 is 68 Fahrenheit. For these last little things, just kind of be aware that there are different scales of temperature, and you should be kind of okay with these three words, conduction, convection, and radiation. But really the guts of it is doing the math of the MC delta T stuff, and of course the stuff we did earlier, conservation of energy with EG and EK. That's it for week 2. Hope it wasn't too bad to go through it online. And sorry, week 3, and we'll see you next week.